Hi everyone. In this episode of the Bitcoin from Scratch in Python series, we're going to implement all the stuff we talked about last time. So we have here some Python code defining elliptic curves, a point on an elliptic curve, and specifically what we're going to do in this episode is define this add method. So this double underscore add in Python is basically if we have two instantiations of this class, this add method will evaluate self on the left as the object on the left side of the operator here, and other as the object on the right side. So we're basically just defining how do we add instances of this point class, or how do we add points together. So as we talked about last time, there are three cases we're going to handle for point addition. First, when the points are inverses of each other, next when the points are different, and then lastly when the points are the same, also known as point doubling. In the first case, this should be very simple. This is where self.x is equal to other.x, and self.y is equal to the negative of other.y. So if we go back to our Desmos demo here, this is where a point is reflected over the curve. So this green point reflected down to the symmetrical negative version of itself on the curve. Okay, so in this case, we mentioned last time that we are going to return the identity element. And we still want this to be an instance of the point class, but we will just put none for both the x and y coordinates, and then it's going to be on the same curve as both self and other, so we can return for the curve here. Okay, but this is how we will identify our identity element whenever we see this. Basically just pass through. So a point plus the identity equals itself. In the next case, when the points are different from each other, so we're going to check if self.x does not equal other.x. And we don't need to define anything else about this. We don't need to check the y value. If the x values are different and they're on the same curve, they're going to be, the y values are also different. So these points are not the same. In this case, we need to, as we talked about last time, we need to calculate the slope between them. So this purple line here has a slope between the 2 points, and we can use this line to calculate that third point. So the coordinates of the third point we're aiming for are down here if we were adding this blue and green point here. So first let's calculate that slope. As a reminder, we're doing y2 minus y1 equals x2 minus x1. y2 in this case, or the second point we'll think of as the other, and the first point we'll think of as self. So in this case, y2 is other.y minus self.y, and put that in parentheses, divided by other.x minus self.x. So this is the slope between our points. We can call this m, and from here we want to use the equation of the line to calculate the x coordinate of the third point. So again, the equation for the line is y minus y1 equals slope, or m, times x minus x1. Okay, so this is not translated to Python code just yet, but this is the equation we're looking for. But first we need to just calculate this x coordinate. So how do we calculate the x coordinate of the third point, which is here? So how do we calculate the point at which this line intersects the elliptic curve? There's a very actually nice formula for this. I have this Stack Exchange thread open. The formula is the slope squared minus both of the x coordinates. And you can see how this user arrives at this. I did go through sort of the algebra myself. It's a nice exercise if you're curious on how this exactly works. It's pretty simple, just tedious algebra really. But basically you take that point slope form we just talked about. So what they have here is just they added the y over. So I have y minus y1 they just added it to the other side. So we have it in terms of y. They plug it into the elliptic curve expression. So you square this whole thing, set it equal to the right-hand side. And you get, when you combine like terms and FOIL it all out, you get this cubic expression, which ultimately you can simplify down to this, slope squared minus both x coordinates. So that's how we will calculate this x. Let's actually call this x3. So our first 2 points we'll think of as point 1 and point 2. This is x3. And we can do, as we just discovered, the slope squared minus self.x minus other.x. Okay, so then we're going to use this point slope form as well to calculate our y3. So this is our y3. Our y1 and x1 are the self. So this is self.y, self.x. This, as we said, is x3. And in Python, obviously, we can't have an expression like this. We need to add this to the other side of the equation. Okay, so now we have calculated the x and y coordinates of our point. We can return that point with x is x3 and y equals y3. And the curve will always be the same, self.curve. We also forgot to reflect this over the axis. So to do that, we very simply just need to make the y coordinate the opposite of what it previously was. So let's see what this actually looks like in Desmos, just to better visualize what's going on here. So let's calculate that third point as we just did. As we said, the x coordinate will be the slope squared minus x1 minus x2. And expectedly, we have that point where the purple line intersects the elliptic curve here. So that's our x-coordinate. Now all we need to do to calculate our y-coordinate is plug this into the equation of the line, which is here. So if so we can say y equals, we're gonna just add this f of x term over. So we have m times x minus x1 plus f of x1. Okay, and our x in this case is going to be our x value that we just went through. So we'll replace that. And you can see now we have, I can change the colors here to show it better. But you see we have this point defined. So we can just plug this in to maybe visualize it better here. Okay, so this green point is really what we just wrote up in Python code. Okay, so we have our point addition, and then finally we just need to reflect that over the axis, which is just the negative version of it. So really this is what, when we plug an example in, this is what we're hoping will be the result. It's negative 1.9 approximately to 0.21. Okay, and then lastly, let's go through when the points are the same. So or how do we double a point? And this is, if you recall from the last video, when we have a tangent line. So we have 2 points that are on top of each other. We need to get the slope using the derivative of that tangent line at that point. So the way to do this, or as we saw last time, was, so let's turn this example off now, and we can go back to, this was our tangent line example. So at this green point, here's the tangent line intersecting the curve, and we want to calculate now this other intersection. So the way we did this last time was we took the derivative of the Bitcoin curve, which is here, and we evaluated what is the slope at that tangent using that derivative. So one minor change we're going to do this time, instead of using the derivative of when a and b are specifically 0 and 7, we are going to do this more generally for any a and b. So we can just use Wolfram alpha here. I plugged in differentiate, y squared, this is our general elliptic curve formula, y squared equals x cubed plus ax plus b. And we get our derivative is a plus 3x squared all over 2y. Okay, so that's what we're going to do to calculate our slope here. So if the points are the same here, remember, self.x equals other.x, and self.y equals other.y. In this case, we want to use that derivative I just mentioned, which is slope equals 3 times x squared plus a, and actually we need to pull this from our objects here, so self.curve.a, and x should be self.x. And we said this is all over 2 times self.y. Okay, and then from here we actually just want to do the same exact thing. So now what we have is the slope of this line in the same way that we had the slope of this line. It doesn't matter anymore that how we calculated the slope. We just want to find where do these lines intersect the curve. So we don't need any new code to do that. I'll actually just move this code here, our calculation of x and y, into the main execution scope of this function. So we calculate our slope based on these if clauses. Once we have that, we can calculate our x and y in the same way and return that point. So let's test this out. We should now be able to, so I'll just if name is main. Let's define some points. Point 1. Oops. And we can do the same for point 2. We need to actually define our curve first before we define the point. So let's use the Bitcoin curve. We'll be pretty much sticking to the Bitcoin curve exclusively in this series. So let's instantiate the curve class, and A, recall is 7, B, I'm sorry, A is 0, B is 7, and our P, again, we'll talk about this later. We're just going to put this as none for now. We haven't implemented P yet. But we can instantiate these points. Let's do 1 at x equals 1. And if you quick run this through the elliptic curve formula, you have x cubed plus 7, which is, in this case, 8, and then take the square root of that. So we can do 8. The square root is to the 1/2 power. So that's our y. And our curve is going to be the Bitcoin curve. Next, let's do x equals 2. So 2 cubed plus 7 is 8 plus 7 is 15 to the 1/2 power. Oops, 1/2. And our curve, again, is the Bitcoin curve. So now we just want to see what happens when we add these points together. Point 1 plus point 2. We'll call this point 3. And let's just print point 3.x and point 3.y. Okay, so again, we should be expecting here, what was it? We should be expecting this point, which was minus 1.909 and 0.21. So that was the reflection of this third point over the y-axis. Okay, so let's open a command prompt. And we can navigate to this directory. and Python, so elliptic curve. Okay, what do we have here? This is in, oh, I think I forgot. Yeah, we need to m times, okay. Little typo, try this again. Okay, and you see we do have those values we were expecting. So now let's try the other case when we have a tangent line. So maybe we can say 0.4 equals 0.1 plus 0.1. So in this case, this should run through this if clause here and double the point since these are the same. Okay, and we can do .4.x and .4.y. So what should we expect here? We should expect this point, which is approximately negative 1.7 and positive 1.3. Flip it over the y-axis, and we will get negative 1.3 as the y-coordinate. And in fact, that is what we get. Okay, so I think we can be confident that all of that is working correctly. The last thing I want to do before we close out this video is let's just create a function to make sure these points are on the curve that they're instantiated with. So this will just take in self, and the reason we need this function is because we make the assumption in this in this point addition, we make the assumption that these are actually on the curve. Otherwise, it'll throw things off. So all we need to do here is pass these into our elliptic curve function or equation. So this curve should satisfy y squared equals x cubed plus ax plus b. Okay, so let's calculate our left-hand side. It's going to be y squared right-hand side is x cubed plus the curve parameter a plus curve parameter b, and this should have been ax plus b. Okay, so we are just going to make sure that the left-hand side equals the right-hand side and that this satisfies our expected elliptic curve equation. So left-hand side equals right-hand side. Okay, so let's check that. Print a new line. And yeah, let's just print that 0.1. Is on the curve. And then let's also check that maybe one of the results of the additions is also on the curve. So 0.3. And let's see what we get. Okay, we have false here. We must have. Let's just print out the left-hand side and right-hand side here. See if we can diagnose this. Okay, so it's just floating point rounding, basically. So let's just round this to a reasonable number of decimal places. Oops. Not sure what I did there. Okay, so let's yeah, round this to 6 decimal places. Seems to be enough. And we can stop printing this. Oh, okay. Great. Okay, so now we have both of these on the curve. And I think, so let's just check before we do point addition that our points are on the curve, and maybe let's also check that they're on the same curve, because we don't want to add points on different curves. That wouldn't make sense for the math we're doing here. So we should check that self is on curve, and other Yeah, I think this is good for now. Let's just check that they're both on. We'll always be using the Bitcoin curve here, so I don't feel the need to check that that's the case. Maybe you would want to if you were using this more generally. But let's just make sure that these points are both on the curve. So if not, we will raise a, we can just raise a type error. Points are not on curve. And let's also just make sure that these are, instances of the point class, which we can't add anything that, we can't do point addition on things that are not in the point class, so. Okay. Okay, so if they're not in the point class, we'll just raise an error. We expected objects of class point. I just needed to add not here. So I was accidentally checking that these are in the point class. We need to check if they're not in the point class to raise this error. Okay, so let's, okay, and we see that that is all working correctly now. Okay, so to kind of wrap up this video, we went through all point addition. The next thing we'll need to talk about is this p parameter of the curve, basically the modulus that we will be including, and how we do these same calculations with modular arithmetic instead of in just normal floating point division and math. So that will require some changes. Most of them are simple changes, but the main thing that we need to introduce is, yeah, the concept of division here. So we're dividing in multiple places. You can't do this using modular arithmetic, so we need what's called a modular inverse instead of division. And we will use what's called the extended Euclidean algorithm to actually calculate that modular inverse easily. It's also worth noting that all of the code up to this point so far is completely reversible. So if you use this code as it stands to generate your key pairs in Bitcoin, anybody could reverse calculate them. So we are still useless in terms of, as far as cryptography goes, this code is still useless. But as soon as we introduce that modulus, that's the purpose for it, to make sure that that point addition, point doubling is irreversible. So we will pick up with that modular inverse in the next video, and I'll see you there.